Today's lesson is on electronegativity and bond polarity. So we'll get started with electronegativity. So here is our definition. The measure of the ability of an atom to attract bonding electrons. So I like to think of electronegativity as a pulling power for those bonding electrons. So different elements have different pulling powers pulling the electrons towards themselves. So now we're going to look at that periodic table of electronegativities. So you may have printed it out or you may be looking at your textbook, and that chart is on page 161. So here is the chart of electronegativities. So the little number underneath the element symbol represents the electronegativity value for that element. So what I would like you to do is to look at the chart and find the elements that have the three highest electronegativity values. So you can pause the video and look at the chart to find those elements. Okay, so if you found the elements, we see that fluorine with the value of 4.0 is the most electronegative element on the periodic table. Runner-up, oxygen, the second most electronegative element with a 3.5. And then the next value is 3.0, and both nitrogen and chlorine have that value. So there are four most electronegative elements on the periodic table. And in general, we can see that the least electronegative elements are down here with values of 0.7, 0.9. So our metals have relatively low electronegativity values, and our non-metals have relatively high electronegativity values. And basically, the closer the element is to fluorine, the more electronegative the element is in general. Okay, so let's write that down because that is important. So our top three, so fluorine with a value of 4.0, our most electronegative element. Fluorine has the greatest pulling power. So you can think of it, it's got the biggest guns on the periodic table. It's the strongest. After that, oxygen. And this is really important because we have a lot more compounds that have oxygen in them than fluorine. So oxygen is our second most electronegative element at 3.5. It's got really good pulling power. And then nitrogen and chlorine are the next at 3.0. So there are our top four of the periodic table. So in general, we can say that our non-metals have higher, forgot my H, higher electronegativity values. That word is way too long. And then metals, always the opposite of non-metals. So our metals have the lower. We'll just say En for electronegativity. All right. So now we're going to look at the different bond types. And before we get to that, we're going to look at our chart again, because we're going to be using this chart. And in this chart, we have, if it's printed out, or if you're looking at it on your computer, we have this little graph here, this little bar chart. Bar chart on your textbook, that is on page 176. So in this chart, it's kind of hard to see, but very down here at the bottom, that says non-polar covalent. In the middle, we can see it. It says polar covalent. And up here, you can't see it, but this says ionic. So we're going to look at these three bond types. So far, we've just had covalent and ionic, but we can break covalent bonds into two types, non-polar covalent and polar covalent. So we're going to start with our non-polar covalent bonds. So these bonds, we have an equal or an approximately equal sharing of bonding electrons between two atoms. So for a nonpolar covalent bond, it means that the difference in electronegativities between the two atoms is from 0.0 to 0.3. And we'll do examples of that so you can understand what that means. Difference means subtraction, and we represent difference by a Greek letter, a capital delta. This symbol means subtract. It means you're looking for the result when you subtract your values. Okay, we're also going to be looking at the percent ionic character, and we're going to use that little bar chart for that. And the percent ionic character for a non-polar covalent bond is from 0 to 5%. Okay, so we'll do our examples here. So first we'll just look at a molecule of hydrogen. Hydrogen has one bond. So when we look at H2, we have an H bonded to an H. So we have these two electrons here that the hydrogens are sharing, and each hydrogen is pulling on those electrons, attracting it to itself. If we look at our chart of periodic table electronegativities, we can see that hydrogen has a value of 2.1. And then this hydrogen, of course, would have the same value of 2.1. So our delta, subtract them, we get 0.0. So if we look on that little chart, right here, this is what we're looking at. That's the one, I forget what page it's on. So if we have a difference of 0, difference in electronegativity, that's on this side, it means we have a non-polar covalent bond, and our percent ionic character, which is on this side, is 0%. So we have a non-polar covalent bond, and we have 0% ionic character. That means it's completely nonpolar. So it would be like a tug of war between the hydrogens, and they're exactly even. Okay, so let's take another example. So the bond between sulfur and selenium. And here we're not talking about a molecule. This could just be one bond in a molecule with many bonds, but we're looking at individual bonds today. Later, we'll look at entire molecules. Okay, so we're going to check our periodic table for electronegativities. And sulfur has a value of 2.5. And selenium has a value of 2.4. So when we look at the delta, and always just take the larger minus the smaller, we have a difference of 0.1. So if we look again at our chart, look at that bar chart over here. So our difference is 0.1, so it's in the nonpolar covalent bond range. And then our percent ionic character, we're just going to estimate it. So if we're at 0.1 here, we're just going to go over, so it's about 1 to 2%. So we have about If you have 2%, that's fine. We're just estimating here. Ionic character. And both of these are non-polar covalent bonds. So approximately equal sharing of electrons. This one's a little different, but we're saying it's good enough. Approximately equal. All right, our next bond type then is polar covalent bonds. So here we have unequal sharing of those bonding electrons. Unequal sharing of bonding electrons between our two atoms. And for this bond type, we have an electronegativity difference. Electronegativity difference of 0.4 to 1.7. And our ionic character, percent, our percent ionic character is between 6 and 50%. All right, now we have a little more to talk about with our polar covalent bonds. The more electronegative element, the one with the higher value, gets a partial negative charge. The more electronegative element has more pulling power for those bonding electrons. So it's pulling those electrons towards itself. And because it does that, it gets to be a little more negative than it would be if it was by itself. And the symbol that we use for that is the lowercase Greek letter delta, which is kind of like a squiggly thing like that, and then we put a minus. So this means a partial negative charge, not a full charge, just a partial negative charge. And then the less electronegative element, we'll just use En for electronegative, gets a partial, of course the opposite, positive charge, because those electrons are being pulled away from it by the more electronegative or the stronger element. And we represent that by a lowercase delta plus. So as a result of this, our bond has what is called a dipole. So that's where polar comes from. So just like we have a north pole and a south pole, a dipole has two opposite ends. So a dipole is when we have equal but opposite charges separated by a short distance, like a bond length distance. And the way that we're going to represent that, we represent a dipole with an arrow. We make like a little plus there. So this plus represents our partial positive, our delta plus end of the dipole, and that goes to the negative end, or the delta minus end of the dipole. So when we have a polar bond, it will be positive near the less electronegative element and negative near the more electronegative element. So let's do an example for our polar covalent bond. So for our example, we're going to look at the bond between carbon and oxygen. So again, we're not saying that's a molecule, we're just saying that is a bond in a molecule. Could have many other bonds. So we're going to do the same process that we did earlier. So we're going to consult our periodic table of electronegativities and write down the electronegativity values. So we look on our chart for carbon, and we see carbon has a value of 2.5. And then oxygen, our second most electronegative element on the periodic table, has a value of 3.5. So then we check the difference. So we'll always take the larger one minus the smaller. So 3.5 minus 2.5, we have a difference, a capital delta, of 1.0. So now we're going to look at our chart. And at the bottom. So this is where our difference is. So we're just going to estimate where 1.0 is. It's in between 0.3 and 1.7. And it tells us our bond is polar covalent. And then we're just going to estimate what our percent ionic character is by estimating where 1.0 is, going across to this side, and I don't know, maybe around 35%. Okay, so this tells us that we have a polar covalent bond and about 35% ionic character. So now, because we have a polar covalent bond, we're going to put a delta plus and delta minus on top of the appropriate atom. So our more electronegative element gets the partial negative charge, the lowercase delta minus. And the lesser electronegative element gets the partial positive charge, the lowercase delta plus. And then to show the dipole of this bond, we go from the positive to the negative, and it looks like that. So that is a polar covalent bond. These electrons between the two atoms are not being shared equally. In a tug of war, oxygen is stronger than carbon and is pulling those electrons towards itself and ending up a little more negative than it would be if it was by itself. All right, and then lastly, we're going to look at ionic bonds. Okay, so as we learned before, ionic bonds, we have a transfer. To make an ionic bond, we have a transfer of valence electrons from a metal atom to a non-metal atom. So for our ionic bonds, our electronegativity difference is greater than 1.7, and our percent ionic character is then greater than 50%. All right, so let's look at an example of this. So example, if we have sodium chloride. Sodium is a metal, chlorine is a nonmetal, and if we have a bond between those, we're going to look on our table for the electronegativity value for each of these elements. So sodium has a 0.9 value. Chlorine's up there in the big 4 for electronegativities. It's got a value of 3.0. So now we do our delta, just take the larger minus the smaller, and we get a value of 2.1. So now we check our table with that little chart. So over here is for our difference in electronegativity. So it's greater than 1.7, less than 3.3. So just kind of estimate where it is and go over here and then estimate its percent ionic character. So it is falling in the ionic bond range. And the percent ionic character, and I'll have to look at that again. Okay, so it's telling us we have an ionic bond and our percent ionic character. Oh, let's see. So let's say about 75%. Now, with an ionic bond, we have a full transfer of electrons. So our more electronegative element gets a full negative charge. So we look at Na and Cl. The chlorine gets a full negative charge, and our less electronegative element gets a full positive charge. So for polar covalent, we have partial charges represented with that lowercase delta, and for ionic, we have full charges. All right, so for your assignment today, you have a list of bonds, and for each one, you're going to do exactly this process. You're going to put the electronegative values underneath the appropriate element, do the delta, get a value, go to your chart here, figure out where the electronegativity difference puts you. Are you nonpolar covalent, polar covalent, or ionic? Write that down. Go over, estimate your percentage ionic character. And then if it's polar covalent, you're going to put in the delta plus, delta minus. The larger electronegativity value gets the delta minus. If it's ionic, you're going to put in a full plus and a full minus. And if it's ionic, and if it's nonpolar covalent, you don't put in anything. So if it's up here, full plus, full minus, delta plus, delta minus, and here, nothing, because the electrons are being shared equally. That's it.